Now, students, we will see some problems based on second normal form. So there are different, versions, or there are different variations. So I've put it in a very simple way. And this problem you can think of, there is a relation R A B C D having attributes A B C D. Four attributes are there, and two set of functional dependencies are there. So we have to decompose this given relation with set of functional dependency in 2NF. So from where we can start, always never ever forget, we have to start with 1NF. So is this relation in 1NF? The answer is yes, this relation is in 1NF. How come it is in 1NF, students? Because when you are putting in a mathematical form, so in mathematical form, composite attributes and multi-valued attributes are not at all allowed. So this relation by definition, or you can say from the relational database, this relation is in 1NF. So no need to check for the 1NF. You can write it, the given relation is in 1NF, first normal form, right? And then you have to apply the second normal form. Second normal form you have to apply. And what is the first step? Now we can go step by step also. What is the first step for the second normal form? Obviously you have to search for the partial dependencies. So PDs you have to search for, and for searching the PDs, other steps are also required. For example, the very first step obviously would be what? Computation of the candidate keys. Now here, if you see how many attributes are there, four attributes are there. So if you're trying to find out from the brute force approach all the attributes or all the candidate key, it would be like this: A, B, C, D, and then you have to go for A, B, okay, and then you have to go for A, C, and then A, D. All the combinations you have to make until A, B, C, D, right? So this is a lengthy approach, but you can follow that, and you can always test this approach also. This approach is called brute force approach. Another thing that another approach that you can follow is left hand side. You have to pick up from the left hand side, and one by one you have to test it. Only two things are there, so you have to test only for the two things. So if you take the first functional dependency, it is saying AB. Okay, now if you try to compute the closure set AB plus, it would give you what? A and B, and with this AB, I can use this functional dependency, and then I can write C also here. And with this B determining D, I can write the functional dependency. What I can write the functional dependency, B determines D, I can write D, right? So luckily I got in a first shot this candidate key. Now I have to go for B plus also. So B plus, if you go, so you can have B, and then you can determine D, but you can't determine A and you can't determine C. So this is not a candidate key. This is not a candidate key. Just for your satisfaction, you can go for AC also, and you can go for AD also. Let me give you thing AC. So AC is determining what? A and C. So it is stopping at this point. And AD is determining what? AD is determining only AD. Okay, you can try for that, and you can go for ACD also, ACD also. So that you have to check. So ACD, if you come here, so it will give you only A, C, and D. So that means it is not giving any kind of a candidate key, because B is missing in that. And if you are trying to compute A, B, C, that will be what? A super key. It will be a superset of this, and then it will become what? A super key. So we are not interested in the super keys, we are only interested in the candidate key. So I have only this candidate key, CK, CK candidate key, and this candidate key is what? AB. So I can write now prime attributes, right? What are the prime attributes? Many students, they would do a mistake like this. In prime attributes, they will take all the attributes because they think that they are the attributes, because we have taken the closure set. Okay, please wait, students, have some patience. AB is a candidate key, right? AB is a candidate key. So prime attributes would be what? AB only. These are the prime attributes. Now what about the non-prime attributes? So non-prime attributes would be what? Non-prime. Rest of the attributes will become what? Non-prime. So here non-prime attributes are C and D. So these are the non-prime attributes, right? So we have identified prime attributes and we have identified the non-prime attributes also. I would request one thing, because only. So you have to follow a systematic approach. First, go with the candidate key, try all possibilities, and then finally discover the candidate key that we have already discovered, AB. Then compute the prime attribute, and then compute the non-prime attributes. Right now, in this case, after computing the prime attributes and non-prime attributes, we have to check one by one. Is this a partial dependency? Is this a partial dependency? AB is determining C. No, it is not a partial dependency. How come it is not a partial dependency? Because it's a complete candidate key. It's a complete candidate key. And this B is a prime attribute, and it is determining D, which is non-prime attribute. So it's a part. You can see that B is a part of candidate key. So it's a partial attribute, or it's a part of the candidate key. So this will become what? A partial dependency. So this is a partial dependency, and it creates a problem. It creates a problem. And the problem, we have already seen what kind of a problem it can create. Now, how can we decompose this relation into a second normal form? Second normal form. The process is same. Now here I would repeat, and now you have to understand slowly. So our relation is A, B, C, D, and this is not a partial dependency, but this is a partial dependency. This PD is a partial dependency for B determine D. So where is the problem? B is determining D is a problem. Now you have to rewrite like this: R, A, B, C, D, right? And then you have to compute B plus, because B is determining D, it is creating a problem. So B plus is the closure set of attributes. So what it will give you? It will give you B, and it will give you what? D. Just check any other thing it is giving. No, it is not giving any other thing. So what are the attributes that I can minus from this? I can minus B and I can minus D. And here I can write it relation 2, in which how many attributes are there? B and D would be there in my second relation. How many attributes are remaining? A is remaining and C is remaining. So in relation 1, you would have A and C, A and C, but you must have one common attribute also. And what can be the common attribute? Obviously it should be a candidate key. And here if you see, B is determining D as a B is a candidate key in this case. Earlier it was a problem, now it has become a hero in this a small relation. So A, C, or you can write it B. Okay, so final decomposition I would write here. This is the final decomposition. Relation 1 is having A, C, and B, and relation 2 is having what? B and D. B and D, right? And what is the common attribute between these two? B is a common attribute, and it is a candidate key in this relation. And with this candidate key, you can retrieve the original data just by taking a natural join, So no information is lost, and this decomposition is called lossless decomposition. And just for your information, one more thing. In relation to, I can write it B is determining D. This functional dependency is valid. And in this relation, I can write like this: AB is determining what? C. So this is also valid. So all the functional dependencies are covered. So I will call it lossless decomposition, and I will also call it functional dependency preserving. Okay, preserving. So what is the meaning of functional dependency preserving? All the functional dependencies are preserved. Nothing is lost in this. Our major, this is a secondary criteria. If you are achieving this, that means you have the bestest of the decomposition. This decomposition is excellent decomposition. No functional dependency is lost, and even no lossless decomposition, lossy decomposition is there. Right, students? So this is the final answer. Finally, you can write it lossless decomposition, and finally you can write it functional dependency preserving also. Okay, students. So see the next set of problems. The same problem is there, but the relation is slightly more complex. So in this case, you have a relation A, B, C, D, E, and the functional dependencies are A is determining B, B is determining E, and C is determining D. And you have to decompose into 2NF, right? So again, this given relation is already in 1NF. It is already in 1NF. So this test is not required. Now the next thing is you have to check for the partial dependencies. And for checking the partial dependency, how you can start? You have to start with computation of the candidate key. But there is a problem actually. The number of attributes are quite higher. So if you're trying to make a combination like A, B, C, D, or E, so it will take a lot of time. So we'll follow the same pattern that we have followed earlier. First we'll check the candidate keys on the left hand side, right? So left hand side, if you try to find out A plus, I think it is not going to give you a candidate key. It is not going to give you A, B, C, D, E. So you can try yourself. And then if you try to find out B plus also, it is not going to give you all the attributes. And if you try to find out C plus, then again it is not going to give you all the attributes. So again, we are stuck into this situation where whatever is on the left hand side is not giving us any candidate key. So what we can do, students, the process one level we have to go ahead, and here what we will do, whatever is on the left hand side, we'll try to make a combination of only those. So we have the option of making AB, and we have the option of making AC, and we have the option of making BC. So if you try AB, I think again it is not going to give you the complete set of attributes. You can try. And if you go for BC also, again, it is not going to give you all the set of attributes. So again, they are not candidate keys. But if you go for AC plus, and if you try for AC plus, let me write this. So AC, we'll start with AC, and A is giving B, A is determining B, so I can include B. B is determining E, so I can include E also, and C is determining D. So C is already there, so I can write it D also here. So we have got a one candidate key AC, and this is the only candidate key in this relation. You can go for the other combinations also, and ultimately you will find that AC is a candidate key in this case. So once we got the candidate key, now I can write the prime attributes. So for prime attributes, I will write like this: prime attributes. So what are the prime attributes? Remember, uh, these are not the prime attributes. They are determined by the AC. So A and C are the only prime attributes here. Then what about the non-prime attributes? So non-prime will become rest of the attributes. So non-prime rest of the attributes, you would go for B, and you would go for D, and you would go for E. Just minus all the attributes from the prime attribute. Just minus the prime attributes from all the attributes. Rest of the attributes will become what? Non-prime attributes. Now you have this prime attribute and you have this non-prime attribute, so you can check for the partial dependencies. So what is a partial dependency here? So for that we need to write a candidate key, and we have determined that AC is a candidate key. So A is a part of candidate key. Yes, A is a part of candidate key, and it is determining what? B. B is a non-prime attribute. So you can see here B is a non-prime attribute. So this is problematic for partial dependency. Now B is what? A non-prime attribute, and E is also non-prime attribute. So this is not a partial dependency. So right now it is not creating any problem. Now again I would write here AC, which is a candidate key. So C is a part of candidate key, and it is determining what? D, which is what? Again a non-prime attribute. You can check it. D is what? A non-prime attribute. It's written here. So this is what? A partial dependency. So there are two partial dependencies. So how we can decompose this relation, because there are two partial dependencies. So decompose this way. This is one of the way that you can decompose. Start with A, B, C, D, and E, and you take first partial dependency, and this is the first partial dependency. So you try to compute the closure of A, uh, and A plus will give you what? A, and then it will also give you B, and because of B determine E, it will also give you E. So three things it is giving, three things it is giving. So right now only we are solving what? This problem, only one partial dependency we are solving. Step by step we'll do. So you can remove this if you are decomposing. A you can cut it, then B you can cut it, and then E also you can cut it. So what is remaining in this relation if you are forming R2 relation? So obviously CD is remaining, and one more attribute will come, and this R1 relation you have taken A, B and E. So this decomposition you have done, but there is no common attribute. So what is a common attribute here? The common attribute must be a candidate key. So obviously this A, B, E, because A plus is determining A, B, E, so it is a candidate key. So you can write here is A, you can write here is A. How you can write it here? A is because A is determining B and B is determining what? E in this sub relation. So the common attribute will become what? A. Now let me further write. We have got two relation. One is R1, which is having A, B and E, right? And I am also having a relation R2, which is having A, C and D, right? And in this relation R1, I am having two functional dependencies. A is determining B and B is determining E. This is the functional dependency that I'm having. But remember, one of the problem is C determines D. Still, it's a problem because it's a partial dependency. So further, we have to solve this. And how can we solve this? Now the problems is quite easy. C plus, if you are trying to find out, it will give C and D, right? It will give C and D. So you have to cut it C and you have to cut it D. So first relation you would write like this R22, and in this you would write CD, and remaining attributes you would write it in R21, and remaining attribute is A. Remaining attribute is A. So what should be the common attribute between this? Uh, between this, and the common attribute must be the candidate key. So candidate key here is C, so you have to take this AC, right? So you have actually decomposed this further sub relation into R21 and R22, and further you have this AC and CD. Now what functional dependency you can write it here? You can write it here C determines D. So this is the one final, this is second final, and this is third final. So if you want to write, it would be like this. It would be like this: A, B and E. This is the first relation, and here you would write A determines B, and here you would write B determines E. This you will write. And then the second relation that you have formed, R21 you are calling it, and here you can write it A and C. And A and C, I think there is no functional dependencies there, so you can leave it as it is. Now the third one is what you are calling here, what you are writing here, C and D. So you would write C determine D, and this way this decomposition is lossless as well as functional dependency preserving. How come it is functional dependency preserving? Because it is preserved and it is also preserved and it is also preserved. So this is the final answer. And if you take a natural join among these three, you will have this relation. You will write it here: A, B, C, D, and E. Did I miss anything? A, B, C, D, E. So this is not required. So if you take a natural join of these three, or among these three, so you will get the final relation that you have decomposed. But in this decomposed relation, you don't have any partial dependency and you don't have any other problem. Any other problem, I mean up to 2NF, this is decomposed. This is decomposed. So this is the final solution for this problem. Okay, students, thank you.